Good morning, everybody. Welcome to another edition of NovaTech's Power Hour. Today, myself, Chi Carnegie, and with Saurabh Rajpal, we will be going through SCADA 101. So oddly enough, we've been doing Power Hour for about 5 years now, since COVID time, and we've never done a SCADA 101 course or a webinar. And so we've been doing a lot of basic courses such as DNP, Modbus, and so on. So a few of our customers have suggested that we do a SCADA 101 webinar. Just want to kind of prep everyone. This is a very basic webinar. It's going to go through basic terminologies, concepts, lots of acronyms. Anyone who's been in this industry, you're aware there's a lot of acronyms. And the way we kind of design this webinar is as if when we were just came out of school as a naive new grad, and you're put into this industry, what would have helped us just kind of learning what SCADA is, or what is the big picture. I myself, when I first came out of engineering school, I was brought on as a SCADA engineer. Very new, very naive, and I think my first day on my desk was a relay and in RTU, and I was asked to make a talk with a set of manuals. And so, obviously this is the best way to learn, just to dig in deep and figure it out, but it would have been nice to know what the big picture looked like, why these devices need to talk, why is it important for them to talk, and why are we using these protocols and so on, and these settings and all that stuff. So the idea of today is to kind of help with anyone who is kind of new to the quote unquote SCADA world, or if you've been in the industry for many, many years and it's a refresher. What is the basic concepts? So just a reminder, all of our power hours we can provide professional development hours. So if you are in need of those, please feel free to reach out to us and we can provide a certificate. And during this webinar, there is a question panel that you have access to. GoToWebinar kind of changed their interface recently, so it's for anyone who were familiar with the old interface. Now it's slightly different. The question panel will be on your top right corner with the big question mark there. Feel free to ask us questions while we're going through the presentation. If I'm presenting, Saurabh will monitor the questions. If we can answer it quickly, we will directly to you, the back in the panel. Or if it's something that we need to go and research and look up, we'll either reach out to you directly, or we will post the question and answer in our post-webinar email. Those emails usually come out about a week after our webinar, and also all our webinars are recorded and get posted on our Power community site. So if you need to share this with somebody else that couldn't attend today, feel free to send the link to them. They will have to register for the Power community website, and we'll talk about that at the end of the presentation. All right, so agenda today, very basic. What is SCADA? What are the components? Standard architecture. SCADA consists of communication. So what are some of the methods, some various applications, and then we're going to go into a little bit deeper of different devices in a SCADA system, your relays, your meters, your RTUs. As I mentioned just a little bit, protocol is a big part of SCADA. So what are the industry standard protocols? Why is it needed to be converted? Some terms that you'll hear, and you've probably have heard if you've been working in the SCADA world: client server, master slave, peer-to-peer. And then lastly, we'll go through why it is important to have time distribution within your SCADA system. All right, down to the roots of it all. What does SCADA stand for? So it stands for Supervisory Control and Data Acquisition. big acronym there. Really, the two keywords I really focus on is data and control. Really, at the end of the day, any system has your inputs and your outputs. Your data is your inputs, outputs your control. And in order to to monitor your system or to have an efficient system, you need to be able to have the data coming in. So before I even go into deep of what a modern day SCADA system is, because most of the presentation today talks about, computing system, advanced communication, more and smart devices. But at the end of the day, at least in our industry, so most of our attendees here are in the power and generation distribution industry. We've always had SCADA. It just might have looked a little bit different. What did old SCADA look like? If you didn't have the ability to see what your system was, how did you know there was an outage? So usually a customer calling in, that's your input. That's your customer saying, hey, my power's out. There's a failure. So that's old SCADA in a sense, right? What about operations? You used to have manned substations. So someone would be at the substation 24 hours to operate equipment if something happened. Or you send out a team to drive to operate equipment. So that's quote unquote old SCADA. But in today's presentation, we're talking about more modern day SCADA. And what does that look like? So modern day SCADA, real-time monitoring. So we have the ability to now have data coming in as super fast, so it's quote unquote real time. We want to have a snapshot of a system. Is the system healthy? Is something abnormal happening? And you want to act on that. If your data is not coming in quick or is quote unquote not real time, or is your decision correct? So you want as real time as possible so that your actions is matches with that. Controlling, to be more specific, ability to do remote control. A lot of modern day SCADA system you can send out a signal to operate your equipment. You don't have to send anyone out anymore. That not only helps with efficiency, but also help with lowering your operation costs. You're not sending a team out, or even safety purpose. Someone operating a larger equipment nearby can be unsafe in the event that equipment fails. So be able to remotely control it can help with safety. Modern day SCADA system has introduced automation. It's not part of the original acronym because there's no automation in there, but it is very big in modern day SCADA system now. And automation, obviously, like with anything in our lives nowadays with AI and so on, does make things a lot quicker. It reduces human errors. Repetitive tasks, we don't want to do the same thing over and over again. And we're now allowed to write rules or a set of conditions to act on certain set of incoming data. So this will help us greatly with our efficiency. Examples of industries that use SCADA. So obviously here, we're all here from the power generation, distribution, transmission side of things, but there's SCADA in water treatment facilities. There's manufacturing, oil and gas, just to name a few, but really big industries have some form of SCADA. They might not call it SCADA, they might call it control system, whatever, but it is a form of SCADA. All right, so why is SCADA important? So I kind of listed a big chunk of it already, but really it is to help with efficiency. So we all, every day, all of us use computers, use phones, and the reason being is computers do things a lot quicker and handle a lot more data. So the ability for a system to handle a collection of large, vast amount of data and make decisions based on it is critical to our system. If something fails, we want actions towards it right away. And yeah, large amount of data. Humans can't do this, right? We can, it would just be very slow, and by the time you make that decision, it's too late. So we want the ability to do things a lot quickly to help with efficiency, better decision making. Not only can a modern day SCADA system analyze a large amount of data, it can also store a large amount of data. So you can store years and years worth of data, and this can help with predictive maintenance. So, for example, with data, you can kind of graph it, see trends. If, for example, 5 years ago you had a transformer blow up, were there data that led up to that situation? Now you can go and monitor for that kind of trend and perform maintenance on that transformer or replace it and so on. This will help ensure that that transformer is safe and is operating properly. Again, lowering the cost of your operation so that you're not replacing a blown up transformer. The ability to know where a fault happened or a failure happened in your system is critical. Ability to send your field technicians out to fix the issue, to minimize outage time, can lower your cost of your operation. Obviously, you want to make your customers happy. The outage time should be short, so reduce downtime. You can streamline your operations now. You can make your system more efficient in the sense now you can start trending when is your peak hours, when is your lowest. So now you can provide power, the correct amount of power to your peak and your low hours as well, so that it's efficient. You can now use, for example, if anyone's seen our previous power hour, we've talked about various logic. You can now operate cap bank controls so that you're not wearing them out over time, or or do it more quickly so that your system's balanced. Safety, as I mentioned, it's important. Obviously, we want our employees and our customers to be safe. So in any form of system that can help prevent equipment from failing, or to help with maintaining those equipment on time before it fails, trigger alarms, detect anomalies, all of that helps with safety. And then in today's world, compliance, everything needs to follow regulations. You need compliance. So with a SCADA system, now you can have the ability to record your data, record, when something's maintained, when the field went out to fix something, provide reports. This keeps track of your system and provide proof that, hey, if something does happen, we follow regulations, we have these records. All right, so now we're going to go into components of SCADA. So we can go all the way down to small devices and all the way up to big devices and so on. So small devices, simple as a sensor. So this is any device that can collect data. This could be, on your power line, could be on your transformers, reading temperatures, your breakers, and so on. So these are any device that detects collects the data. Actuators are devices that actually does the actions, right? The device that can open and closing breakers, the switches, adjusting levers, for example. So these are your field devices. And then, and you've all heard these IADs, intelligent electronic devices. So these are smart devices that monitor and control and protect your equipment. For example of IADs are your protective relays, your meters, I/O modules, circuit breaker controllers, voltage regulators. These are all smart devices out in the field or in your substations. PLC, so lots of acronyms as I mentioned. Programmable logic controller. So any device that you can write logic into it. So you can write, predefined rules to act upon certain conditions. These could be in the form of, ladder logic, function block, scripting, coding. Anyone who's used RLUA, that's a form of programmable logic. And then remote terminal unit, RTU. So this I need to kind of dig a little bit in deeper. Saurabh will go through it as well. But the terminology I want to kind of clarify, because I got confused as when I was a new grad, because remote terminal unit, the definition of it is the actual computer, the electronic device that, you know, collects data, that pulls data from your IDs, and your IO modules, and it can do logic in it, it can convert the protocols, and it can send up to your control system. So that's what a RTU is. What confused me previously is sometimes people call RTU the whole cabinet, the RTU, and you know, and I think it's just terminology wise, people do it all the time, and people, it's fine, but I just wanted to clarify because I got confused. And so really a RTU cabinet is that it's the cabinet that has the RTU device in it, but the cabinet itself should just not be called an RTU. It should be called an RTU cabinet. The RTU cabinet usually contain an RTU device. So for example, NovaTech's Orion is an RTU device, and in that cabinet usually has your switch, your routers, your terminal blocks, your IO modules, your touch screen for your HMI, and so on. And that makes up of the whole cabinet. But I just want to clarify, the device itself is the RTU, remote terminal unit itself. Human machine interface. So this is quite important because you have so much data coming into your system, and no human, no technicians, no engineers can analyze all that data quickly. So you want to present that data in more of a user-friendly format. So for example, a one-line diagram, an alarm annunciator. You want the ability for a human to interact with the system. So, you know, web UI is a form of HMI. How to send controls, how to set a parameter. Those are all HMIs within the system. So it's ability for, you know, a human to interact with your SCADA system. So another thing that I want to bring up, SCADA, again, I always thought SCADA was, you know, the top level, and we'll go through that too. But SCADA systems actually consists of, you know, like I already said, it's not only the system that shows the data and so on. It's entire system where include the field devices that we just mentioned. But one of the critical thing is, hey, how do I get data from point A to point B? This is your communication infrastructure. This is the backbone of SCADA system. If there's no communication infrastructure, there's no SCADA system. Your SCADA software at the top is kind of useless if there's no data coming into it. So communication infrastructure could be your wired, your Ethernet, your serial, your fiber, your radio, your cellular is your wireless form of communication. But you need to also make sure that, hey, because the data is coming in and controls or actions are depending on that data, you need to make sure your communication is reliable. So, and we talk about real-time connectivity. It needs to be fast. If the data is delayed, are your actions correct if the data is delayed? So depending on your system, and if it is very critical and important, there might be redundancy built into your communication. There could be your primary and your secondary lines, automatic failovers or loop, and so on. So there's many communication network out there. And then obviously with this now day and age, security is very important. So, you know, we need to make sure our data is encrypted. Is there firewall settings? There's VPNs to help you safeguard against unauthorized access. So this all makes up SCADA as well. Now the control center. So this is what I always thought, again, as a naive new grad. I always thought SCADA was just the control center. Its control center is obviously a big part of it, but it is just a component of it. And control center can be different from utility to utility. A big utility can have a huge screen like shown on here, and it has all your substations, which could be, you know, 50 plus substations or hundreds of substations, and they're using HMI. They can graphically show in a user-friendly way to know that, hey, everything's normal or something's abnormal. But if you're a small municipality or co-op, your SCADA system, your control center might be a little bit different. It could be a few monitors monitoring a dozen of substations. So that still is a control center. It's anything that kind of have all the data coming to. Your control center obviously can do controls, and then there can be automation associated with within there as well. So as I mentioned, you can have automation in the field, but now you can also have automation at the top of your control center. One other thing is to be able to know something's abnormal. So alarm management is critical part of the control center. When is something exceeds a threshold, it triggers an alarm, notify the operator. The operator can now call a field technicians or engineers to go to a certain location to fix that issue. The control center can also record the alarms, the events, keep tracks of faults. And over time, it can improve corrective actions. So again, back to predictive maintenance. Data historian analysis is usually a part of the control center. Helps with analysis, can help troubleshooting, reporting, identify trends, optimize operations. So really, again, just to be able to see what happened historically in the past to prevent from future issues from happening. And one big thing about a control center SCADA system is ability to integrate with other systems. And you've all heard this. You got ability to integrate with asset management, your ADMS, your outage management system, GIS, weather forecast, all that stuff to improve to be able to improve your system and provide information to those systems as well. Billing system is a part of the integration. And just kind of provide an overview of all those components that we just went through. Really, at the end of the day, field devices, very general here in this diagram. Data flow goes to control center. Anything in between has your communication infrastructure. And as much as I said, hey, computers are great, we do need operators at our control center. They're the one that, hey, when something's abnormal happening, they have the final check, the final say. If something didn't happen in the sense automation wise, if a breaker was supposed to open via automation and it didn't, the operator can see that and now can send out a group of technicians or field guys to go and look at it. So at the end of the day, we do still need human intervention. That's our operators. Standard architecture. So this is obviously, there's many architecture out there. This is just a common one that we see with our projects and so on. So I just want to provide a kind of very, very generic architecture, usually is multi-tiered. What we usually see is, there's an RTU at every substation. If it's a big substation, you can have multiple RTUs. Field devices, your meters, your relays, data is going into your RTU. The RTU, as mentioned, can have built-in logic there and can operate the field devices accordingly. And then RTU does protocol conversion. And so if data is coming in to the RTU is Modbus, it now can convert that data to your control center using DNP3 or other protocols. So usually this is what we see. Obviously, it can be different in other applications, which we'll go through in a bit. But at the end of the day, most data goes to the control center. Again, depending on your company standard, not all data goes to the control center. The RTU can kind of parse out the critical data and then send to the control center. So maybe only 20% of the data that's in the RTU goes to the control center. So it's really up to your company standard. All right, back to the basics. As I mentioned, part of my first task was to get two devices talking to each other, and one of those tasks was hey, get them to talk serially, get them to talk via Ethernet. And so, like I said, this is a beginner's course, so I want a refresher to everyone. What are some of the communication methods you might see? We still see serial a lot at the substation. So I want to kind of go overview what are some of the serial communications we've seen. RS-232 and RS-485 is pretty common. As a refresher, if people don't know the difference in that, 232 is peer-to-peer, so one device to another. So you got your one client and then your one device that serves data to it. It transmits 1 bit at a time. Baud rate, you hear baud rate a lot in serial communication. 9600 is pretty common. That means 9600 bits per second. Connectors wise, the one in the picture here is the DB9. Some serial RS-232s are DB25s. You might even see RJ45, which is this cable, which is confusing because it looks like an Ethernet, but is actually serial. So very rare, but it does happen. You see RJ45 connectors in a serial communication. RS-232 is usually for short range, mostly because it's very susceptible to noise. RS-485, very different from 232, is that it has the ability to do multi-dropping. What that means is that for one serial connection, you can have multiple devices onto that. RS-485 standard calls up to 32 devices. And so as long as those devices have unique addressing, so for DNP or Modbus, they should have unique addressing so that the client can differentiate what data is coming from what device, but it's on the same serial channel. There's two forms of RS-485, it's 2-wire and 4-wire. 2-wire is half duplex. It means that device can only transmit or receive at any point in time. They can't do both. 4-wire is also known as full duplex, and it can transmit and receive at the same time. It means communication is a lot faster. So anyone who's ever worked with our Orion MX, the serial ports on the MX is software selectable between RS-232 and 485. And when you go into the web UI of it and you select which one, 485, you'll see the 2-wire and the 4-wire mode there. Serial fiber. This one confused me a little bit as a new engineer. I always thought fiber was Ethernet, and then until I realized there is such thing as serial fiber. So similar to 232.45, you're still dealing with baud rates. It's not network. It's not Ethernet. There's no IP address associated with it. It's point-to-point, similar to RS-232 in that method. Because it's fiber, it transmits light pulses. Is high-speed communication. It is better for long distance, and unlike 232, it is immune to noise. Now we'll switch over to Ethernet. So Ethernet is network communication. So anytime you put in the IP address, that's an Ethernet communication. So most common one you'll see at your substation will be your copper. So that's your Cat5 and 6 cables there with the RJ5 connectors. If you have a local network at home, that's what you're using as well. And copper tends to be about speed-wise 10 megabit per second to 10 gigabit per second, and distance-wise about 100 meters. Again, with fiber, now fiber, because of its ability to transmit, it can do longer distance than copper. Faster speed, up to 400 gigabit per second. Fiber is more expensive due to its greater bandwidth and reliability. And again, if you're working with either serial fiber or Ethernet fiber, you'll heard the terms multi-mode and single mode. That's something that we deal with in our products. Multi-modes mean multiple light modes. Usually it's for shorter distance, up to 2 kilometers. And then single mode is one light mode only, and it reduces the light dispersion. So that because of that, it can handle longer distance, so up to 100 kilometers. And now we'll switch over to wireless. So the most basic wireless is your radio. So that's transmitting data using radio waves across various frequencies, and it can be short or long range communication. So if you have pole top devices and so on, you usually have a radio modem in there, and that radio modem is connected to your device serially. So there's usually a device with a serial connection to your radio modem to send that data out. Cellular is more advanced. This is your cell phone technology here. So it uses radio communication, but it's more on private or public network cell towers. And these are your LTEs, your 3Gs, your 4Gs, and your 5Gs. So usually cellular modem will have space for your SIM card. So you would have to purchase a plan with a private or public network, and you will have those SIM cards into your modem. And then lastly, microwave. This is high frequency radio waves. It's more point-to-point communication. It's high bandwidth, high speed, long distance. But one thing is it does require a line of sight, and it does get affected if weather conditions are bad. All right, so SCADA applications. So not to go into detail, but we already kind of talked about it. Local SCADA substation. So there's such thing as local SCADA, and I kind of mentioned it. Your RTU cabinet at your substation is local SCADA. You got your data collection, your data coming in. You got your HMI screen. That's what we mean by local SCADA at the substation. Mini SCADA. This is for what we've seen a lot with our municipalities and co-op customers. They only have a handful of substations. They don't need a full-blown SCADA system. They just need visibility into all their substations. So they have what we call a mini SCADA system, where they still collect the data, they still have their one lines, they have their kind of geographically showing all their substations, and they can still operate and control and do controls onto the remote equipment, but it's just a smaller version of a full-blown SCADA system. There's also distribution automation SCADA system, now monitoring your distribution network with a lot of renewables popping up, solar sites, wind sites, battery energy storage systems, microgrids popping up. Now there's usually a SCADA system for those sites. And then lastly, full-blown SCADA system. That's what we kind of talk about, our control center. These are large-scale implementation. And this is where your OSIs, your Siemens, your ABB, and your GE, those are your full-blown SCADA system. All right, I think I talked plenty. I'm starting to lose my voice, so I'm going to switch over to Saurabh. Saurabh, please take over.
Thank you, Chi. I'm just going to steal the screen here. Okay, so Chi, that was excellent. Thanks for the SCADA overview. And today I will be covering some of the functionality of the relay meter RTU, why they're used, and I'll be touching base on the time synchronization, some of the protocols that's available, and protocol conversions. Okay, let's start. So the protection relay that we have, the primary function is to monitor the electrical system for typically finding pre-fault and fault conditions, so it can isolate the circuit from being further damaged. That's the main purpose for it, so it can isolate the circuit from being further damaged. Then we have the meters, which are typically measuring the electrical parameters such as voltage, current, power, and frequency. So those meter data can also be aggregated to the RTU. The third component we have is the RTU. We touch based a little bit on the RTU. Different people would call it differently. Some would call them gateways, data concentrators, RTUs. The primary goal of RTU is to collect the data from the connected devices, such as relays, meters, and other IEDs from the substations. And then it can transmit the collected data from these devices to a centralized system, such as SCADA or EMS, over different COM methods that we discussed before. Now we will look into this in depth about each of these components. Like we said before, the fault detection is something the primary goal. It identifies faults like short circuits, ground faults, or any imbalances in the phases or ground in the system. It also can isolate the fault by automatically opening or tripping the circuit breaker, so we don't spread the fault further and kind of isolate from the rest of the system. Um, Other function of protective relay is to prevent cascading failures and limit the spread of the damage to other parts of the electrical network. Um, Most of the IEDs have inbuilt alarms and indication capabilities too, whether they're visual or audible, so that system operators can be notified for any abnormal conditions. So on this right-hand side, this is just typical single line diagram. We've got a bus with a breaker and perhaps multiple feeders. It shows here just one, but realistically there'll be multiple feeders. And then we have the CT and PT connected to a relay where the relay can sense based on the configuration and settings, different protective elements such as instantaneous overcurrent, time overcurrent, ground faults, and anything with under over voltage. So depending on what circuit are we trying to protect, there would be different protective elements to protect those equipment. Um, so coming to the types of the protective relay, on the right hand side, we've just shown you a little bit of the devices that we're trying to protect, whether it's a transformer or a bus that we're trying to protect, or a generator, a line, or a feeder protection. So there are various different relays for different functionality, and they vary with different characteristics, whether they're using a differential, distance, over current, directional, under over voltage, under over frequency, and ground fault. So let's take a look at the differential relay. It typically protects transformers and generators from localized faults. It compares like current coming in, entering, and leaving a zone to detect faults within that zone. Um, Moving on to distance, that's typically used as the name defines for distance for transmission lines, and it's an impedance based. Whereas overcurrent relays are used for protecting against overloads and short circuits by detecting excessive current. Moving to directional, used in typical distribution and subtransmission electrical systems. And the over voltage and under voltage are, as the name implies, to ensure the voltage levels remains within the safe limits during faults. Under over frequency is typically used for generator operates within a safe frequency range, and then we have the ground fault protection, which detects the ground faults. So that's about the protective relay in a very high level. Of course, there could be another webinar, I mean, for each one of these elements. So we're just showing you just an overview of what different type of protective elements are there. Moving on to meters, typical are revenue meter, plan check meter, and SCADA meter. The revenue meter is used for billing and energy consumptions, and for compliance purposes too. That the accuracy for these are very precise, just because they are used for billing purposes, and they have to comply to the national standards to make sure the fairness is there for energy billing. It typically, for data collection, it measures over time, and typically in kilowatt hour for revenue generation, and is installed at customers' premises or anywhere there's good connection points. Um, Plan check meter is used for verification and energy audit. So it's basically to cross-checking the operational performance. It kind of serves us just as a backup to the main revenue meter to make sure the compliance is there and it's as accurate as it's saying. So it's kind of like a backup meter, but it also provides uh, during internal audits, you can use the plan check meter to validate what revenue meter is giving. The third one, most common, is SCADA meter. It's used for real-time monitoring and control, and it gets the parameters like voltage, current, power, frequency, and then it's used in conjunction with SCADA. So all these points are fed to the SCADA. So for logging purposes, it continuously logs the energy consumption data for analysis and reporting purposes. Um, and typically used in substations, grid control centers, and distributed power systems. That's the very common SCADA meter we have. Let's take a look at the RTUs. I was briefly mentioning about RTUs. In my past life, I mean, some manufacturers do use name as RTU or data concentrators and gateways. They're somehow very comparable in terms of functionality, but they play a crucial role in real-time monitoring and control. Um, we've jotted down some of the applications that RTU can do. So data concentrator being the most important one. It interfaces with SCADA system for remote monitoring and control, and is typically connected to all the meters, relays, and other substation equipment. So the data actually gets consolidated into an RTU and is concentrated and then fed to the SCADA for visual purposes or control purposes. The second application on the RTU is it also acts as a protocol converter. For example, if you've got something that talks Modbus and then you want to convert it to DNP or 6150, one or the other, ensuring the devices can be interoperable with different languages or standards. So it acts as a protocol converter, and we have a slide in a in later stage. We'll talk about protocol converter. Other aspect is security and firewall. So it ensures that the data which is transmitted between the RTU and SCADA is encrypted. Also provides access control. So whether it's a role base or a radius, different capabilities are there in different RTUs to make sure it's filtering the traffic. It's allowing the network ports or IP address, which are predefined. So that is a must to have. Sometimes we also use RTU as a media converter too, because what happens is you have, for example, you have a physical media, the relays are talking serially, and you want to send fiber over to the SCADA system. So it kind of converts the serial to a fiber or serial to a copper Ethernet. So in an RTU, this typically means converting between like electrical signals to an optical or vice versa, if that's what it's doing. Um, Local HMI, the RTU can be some of the RTUs do provide local HMI that could be used in a typical one substation, for example. That's your eyes to that substation. That means mimicking your single line diagram, all your alarms, annunciators, and all your trip and close, your controls can be done locally. This is a hardware based RTU, so so the HMI is a capability that you can either remote into a particular substation or have someone to go into the substation control center and have a look at the HMI. Time synchronization. This is also another slide we'll talk in detail, but the RTUs are capable of propagating time, whether it's NTP or iRig for the distribution. The RTUs can further send the time signal to the devices it's connected over, whether they are serial or Ethernet. And again, we'll touch base on time sync in a later slide. Um, Alarm notifications, that's important. So you would probably get an alarm, you probably get an SER from the relays that is sending that data. Hey, this is critical event happened, that gets pushed to the RTU, and the RTU you have the capability of alarming it or sending it to the crew there, or perhaps sending an email or text, whatever works for the clients usually. Some RTU do have the access to go to the relay or the meter via engineering access. So the RTU has the capability to tunnel in, to a relay or IED, allowing a personal to go to the RTU and access the end device for configuration, verification, and setting adjustments. Um, the hardware I/O, the RTUs often have some input and output capabilities, whether it's a digital I/O or analog I/O. Some of the examples you would use the digital I/O for discrete status signals would be such as relay contacts or switch position. Any of the discrete status can be also hardwired to the RTU and propagate that to the SCADA. Um, yeah, so and then we have the capability of data archiving and data analysis. So often RTUs have inbuilt memory. So you could have your alarms, or you could have any of these analog values archive, and then monitor, and you can actually use them for analysis purposes once the data is being archived through trending, or if you have a blip in the system that you're not able to detect, then this archive kind of helps you to figure that out. um, Last application for an RTU would be logic engine. I think we touched based on that a little bit. So RTU or PLC generally have different logic engines, whether it's a 61131 logic, which includes the structured text, ladder logic, and CFC. There are other capabilities which are similar to like C language, like Visual Basics or Lua, that you can use to further enhance or further fabricate the data that's going upstream to the SCADA, and or there are capabilities of designing new applications, because once you have your logic engine and you have your data coming from your IEDs, now you have endless option to create your own applications. Okay, so that covers the three major functions for that. Let's move on to protocols and protocols converter. We have a lot of protocols. Here's listed with there's three tabs. One's for SCADA protocols, the other one's for the relay or the meters, and then we have the IT and enterprise protocols. Some of the common protocols on SCADA side are DNP3 or DNP3 secure authentication. In the European side, we have the 101, 104. Modbus is there on the SCADA side, and then if you move on to the relay side or the meter side, typically you've got the DNP 6150 Modbus and some proprietary protocols from SEL. Those are used. And moving on to the IT and enterprise protocols. So to talk to multi-speak and ICCP are more on the SCADA side, and then you've got common IT ones, which are FTP, SFTP for file transfers, the HTTP or HTTPS for web browsing, and then you've also got some of the time sync ones, which are the PTP, SNMP, PTP and NTP. So these are further like a lot of protocols, and we have to ensure that one can talk to another, because we're dealing with so many devices. If you look at the SCADA overall, that has many devices, and not all devices will talk the same language. Hence, you need a protocol conversion, which brings me to the next slide here. Why is there need for protocol conversion? So, like I was saying, different devices and systems support different communication protocols, and to ensure compatibility is essential for seamless exchanges between the devices. So I've got a scenario. So I've got three IEDs. Two of them talks Modbus, one of them talks DNP, and those are sending data to the RTU. An RTU can talk hypothetically a Modbus OPC UA, DNP3, and 6150. So now RTU is able to get the data from Modbus and DNP, but the SCADA only talks DNP3 and OPC UA. So in this condition, the RTU has two ways. One is to get that data from the devices and either send to SCADA via OPC UA or convert it to DNP. So this is just a small example why we would need a protocol conversion, and RTU can do that to ensure that efficiency and reliability in the automation control systems. Our next slide is common terminology between client server, master slave, peer to peer. So in the client server terminology, the client initiates the communication by requesting data or services, and then the server then processes those requests and sends a response. The main thing here is the server can respond to one or more clients, whereas, excuse me, moving to master slave, um, the master controls the communication flows and issues commands, and slave only responds when requested by the master. So there is a limited scalability, and if we had to add more slaves, that would require reconfiguration. And if the master fails, slave becomes inactive. That's in a nutshell the difference between the two. And then we have the peer-to-peer or publisher subscriber. In this scenario, publisher transmits the event change or status continuously, and the subscriber devices listen to those events and actuate based on whatever they need to do. One example of this protocol is 6150 Goose. So it keeps on transmitting that data. Whoever is subscribing to it knows what to do. I like to explain this like just like a radio. So in your car, so FM 99.9 is transmitting a data. Whoever is subscribing to 99.9 gets that data and gets the music or whatever conversation is going on the radio. That's in a nutshell the different architectures we talk about. Let's take a look at the time distribution. Why is time distribution crucial? Well, it's fault detection and restoration. In case of faults, time sync help determines the exact sequence of events from the relay. This aids in quickly identifying and root causing the issue, so that helps in restoring the power system back to uh, stability. So with the pre-fault and post-fault analysis, so if a fault happens in a substation, the time synchronization, if all the devices are not synced to the same device, then it's kind of hard to find what happened and in what sequence the fault happens. So it's important for all the devices to be time synced. Other application why you would need time sync is grid health and stability. The accurate time for synchronization ensures all the components of the grid are operating in unison, and it allows precise coordination for generator transformers and other equipment, which is essential for grid health. I believe synchrophasers is one of the protocol that ensures the grid health of the power system. Um, Data logging, that's also crucial. So once you're archiving data, you want to know they have the right timestamps to have meaningful data. The time should be kind of accurate. So if you have multiple devices, some on UTC, some on local time and different time zone, they may not make sense once you have archived all that data. So it's crucial for you to have a time distribution accordingly. Um, Other categories are for energy trading and market operations. So where market transactions and pricing depend on accurate timing. So they must align their schedules to ensure that they're buying and selling power at the correct times. So those are some of the reasons why you will need time distribution. Now let's take a look how we can distribute time. So often there are more schemes than shown here, but these are most of the common to our industry. So time can be distributed over IRIG-B, NTP, PTP, or IEEE 1588, and or protocol time. So IRIG-B is commonly used to synchronize time in power grids for a control system, as we all know. NTP is widely used protocol to synchronize clock over a computer network. NTP servers often synchronize with GPS clock and then provide the time information to clients over internet or internal networks. One of the advantages of NTP is it's relatively easy to implement, right? And it can be used across large networks with variety of devices. However, in terms of precision, PTP, which is my next point here, is has more accurate time synchronization compared to NTP because it works over sub-microsecond accuracy. And PTP also works by using a master-slave model, where a master clock will send timestamp to slave clocks, and the slave adjusts their clocks based on the received time. So they kind of autocorrect their time based on the slave clocks that they're talking to. Protocol time, again, a master-slave model. The master is typically the time reference. If you're sending the protocol time over RTU, then they will get the RTU time and synchronize the internal clock with the master. This image just shows a physical connection of a typical time distribution model where you would have satellites that is getting through antenna coming to the coaxial cable, going to a surge arrestor to protect against lightning attacks, and then that goes to the clock, and then now you have options for distributing time by various methods. So one would be Ethernet. In that case, you would use NTP, SNTP, or PTP. But if you're using a coaxial or a twisted pair, you can send IRIG-B, including fiber, and then there's a capability of sending a modulated or an unmodulated signal to the devices. And in the IRIG-B, you have the capability of further distributing this using a T channel. You could further distribution time by rack, and again, this has to be calculated based on how many devices you can distribute over IRIG. So yeah, time is important, and we have to ensure all the devices in the substation are synced to some time reference for all these applications. This brings me to the end of the slides. Before we go, I would want to reflect on our community side, which can you can go to novatechautomation.com/community. You would need a sign in if you don't have it. So at the bottom it says sign in. Just put in your work email address, create a password, and you should be able to access the Power Hour, all the recorded ones, including this one. You would go to the community websites for any events, training, any user manuals, drawings, or compliance. So feel free to explore that. Another site is the support site. That's at support.novatechautomation.com. And if you want any of our products, firmwares, whether it's Orion or Bitronics meter or Kronos clocks, any release notes, the software NCD, it's from support site. And the last one is the sales engineer booking. So in case you're looking to set up a time with our sales engineers, we have the sales engineer shown on the bottom right. You can either select any particular one of your choice or whoever's available, and you can book a slot to go through any application that you might want to discuss with us. So that brings to the end of our webinar. Thank you all for attending the webinar. We will be addressing any unanswered questions via email. Thanks, everyone.
Thank you. Bye bye.